get into drives section. So now what we are discussing, basically we are trying to understand how to basically implement the space vector PWM. We understand that, okay, conventional space vector PWM, if someone is asking, we understand somehow that, okay, we are trying to implement this kind of vector sequence R7210, and we know how to compute the time periods T1, T2 and TZ by 2, TZ by 2 we are distributing, and it is operating. But if you actually think, how would you implement this? What comes to your mind? Will you be watching the clock, what is going on, or something else can be helpful over there? So this is where we try to understand that how many samples first we need to create in one sector. So how many times we need to repeat this one of these sequences. That's what we have tried to do in the last class. So what we have understood, that for keeping the symmetry, we need to have one sample at the middle of the sector. That is for sure. And each sample is including like 3 switchings. So if we are having n samples, we are dealing with total number of 3n switchings in the sector. So in one sector, if we have these many switchings, then basically in complete sector, in complete full fundamental cycle, we will have NSW, if I say, for the complete cycle, this will be 6 times of 3n sample, which means 18n sample. So if you compute the pulse number basically the on and off transition, so it will come out to be, for all 3 phases, I am saying, it will turn out to be 18n sam by 2, which is 9n sam. And per phase, the pulse number would be 3 times of n sample. This is what we have established in the other way from the, in the previous class, right? Yes, Deepak, any question?
Sir, that is what my doubt was, that yesterday you have explained that we will put this vector in the center. Like if it is, yes. But my doubt is, like if I see in terms of ripple, then if I put it in center, last time as you have explained for sine wave, at 0 average, the ripple will be maximum. Here also, if it is aligned, let us say very close to vector 1, then in that case, I will have a lesser ripple, na, sir?
Lesser ripple,
like
for
very close to ripple, but I'm not exactly on it. Let us say I'm on 1 degree.
Yeah, 1 degree. But what about this voltage error?
But then this voltage error will be applied for very small time, and then as the difference in the two is very small, then the net ripple current will be very small, na, sir?
That is there, but still, see, when you say it will be very small, but what is the quantification of that very small?
Like, okay, I just started quantifying it. I was just trying to do that exercise. I have not completed it, but roughly what I saw, it was coming smaller value. Like if
okay,
I put
so
it,
what I do, tomorrow we will have the discussion on current ripple in this space vector domain. Then perhaps this point will be clear.
Yes, sir, that will be then giving clarity.
So let us defer this point up to tomorrow, and tomorrow we will discuss this. Why this is better, why this is not better, that we will see tomorrow, right? Okay, as of now, what you consider, that to have some good quality waveform, we should have the samples distributed properly in the sector. So by distribution, what I mean, you definitely keep a sample in the middle of the sector. That means at gamma equals 30 degree. And then we know that the pulse number is related to this number of samples are related to pulse number in this manner. So if we are talking about pulse number 3, then we are going to have only one sample, so which can be located at the middle of the sector. Now if we have pulse number 9, basically we need to have 3 samples in a sector. So apart from keeping one sample in the middle, other 2 can be kept symmetrically around that. And the gap between the two samples could be your sampling angle. So this is your gamma sampling. or let me name this sampling angle as delta. That is better for differentiating between the two. Delta sampling. So this is the angle between two samples, and how we are obtaining that? This delta sample is nothing but 60° divided by n sample per sector we are talking about. So see, another thing is, if you try to keep it very close to this one, the problem is this will become very far from V2. So again you will face the same problem. Okay, and tomorrow when you do the current ripple analysis, in that manner, again you will find that one of them will give very large ripple, another will give little less ripple. So on an average itself, you will see that you are going for higher ripple for the complete case. So everything will get like off shifted towards this point. That's all will happen, nothing more. Correct. And there is one more reason which we will see today, why we are keeping it like this. What is the meaning of basically keeping the sample over here? That little bit more practically we will try to see. Okay, so this is fine. We are keeping it over here, so we can have gamma for these three positions, or samples at these three positions, 10°, 30°, 50°, because our delta comes around 20° for p equals 9. Now I have asked you to solve the gamma values for pulse number 15 and 21, right? Can you quickly tell what are these numbers?
Yes, sir. For 15, sir, pulse number is 6°, 18°, and 30°, 42°, and 54°.
Yes. For 21, someone else need to tell.
Yes, sir. 8 and
4.28,
4.2. Yes.
Someone else, yeah.
4.28, 12.855, 21.485, 30, 38.565, 47.135, and 57.705.
Okay. Something around you are getting, no? These values you are able to compute, right? So
Yes,
7
sir.
samples would come. That is good.
Yes, sir.
So the meaning is, now if you see gamma value, which means at which the samples are located, the value of sector angle, this is fixed for every sector. So which means that for every sector, our computation of T1 and T2 and TZ is going to remain same. You understand my point? If we have said that our samples are located, say pulse number 15 I am operating, and for sector 1 my samples are located at 6, 18, 30, 42, 54. Now the same thing is true for all the sectors 2, 3, 4, 5, 6. Which means I only need to compute these numbers once, TZ and this is T2. So these numbers should be computed only once, and then we are repeating the vector sequence for every sector based on which vectors are forming the boundary of this sector. So which is what we will try to generalize today. Now, okay, this is what we have computed. This is fine. We were trying to understand the meaning of what we are doing basically. Our fundamental voltage vector is rotating. What is the meaning of keeping a sample at 30°? What is the meaning of keeping a sample at 10° or 50°? What's the meaning of that? So here one thing you need to understand, that we are dealing with vector quantities. Meaning of vector quantities, it has magnitude and direction. Before this, when we were doing the per phase analysis, we were only dealing with some scalar quantities where magnitude is enough. We have, let us say, some voltages, say 10 volts positive and 10 volts negative, and we are applying for duration of say 1 second and this for 0.5 second. The average value, we can say we are getting something like, how much will be the average value? 5 by 1.5, right? That would be the average value of this voltage, what we are realizing, correct?
Yes, sir.
Fine. And this is enough. We need not say about where it is located. What we have done, we have applied positive 10 volts for 1 second and negative 10 volt for 0.5 second. And in effect, what we are getting a voltage which is something around, say, 3, how much it would come? 3 something, right? 3 point some volts over here. Now, the same thing you think in terms of quantities which are having direction. If you are applying, say, 0 vector, then for some certain duration, say tz by 2, next moment you started with vector 1, and this you applied for duration t1. Next instant you have applied vector t2, sorry, v2 vector for the duration t2, and then you have applied 0 for another tz by 2. This is what we have done discretely. The resultant of these quantities will be a vector which will have certain magnitude and certain direction based on what is the value of t1 and t2, isn't it? You understand my point?
Yes, sir. Yes, sir.
Yes, sir.
So if I scale this V1 and T1 and V2 and T2, or take product of V1, T1 and V2, T2, it will look something like this, and then a small number, say here like this. So this will be equivalent scaled vector, and this is the another equivalent scaled vector. Rest are 0. The resultant of the two are matching, and this is what it is. So what I'm trying to say that how do you implement a space vector PWM? I'm not saying conventional only, any space vector PWM. How do you implement? You are given a motor, you are given a power converter. How would you implement? Let's say you have to operate for V by F. This is some induction motor. I have asked that, okay, you have to operate V by F, keep pulse number 9 and operate the induction motor in conventional space vector or any space vector PWM. Say, how would you do? What will be the approach? To make things easier, let us say I say that, okay, keeping V by F, operate at 20 Hertz. How would you do that? So this is where our understanding should be that what we need to implement CSV PWM. What do we need? We need to apply appropriate vectors in different sectors. Correct? Yes or no?
Yes, sir. Yes, sir.
These
Yes,
are
sir.
6 vectors which we are going to apply. But based on what? Based on the location of the voltage vector, which means we need to know where the voltage vector is located in this plane. In which of the sector this voltage vector is revolving or rotating. Fine. This is the first information you need. So we need information about the sector. Now, next we need information about the sector angle, at what angle it is at. Then we can compute what are the time durations or dwell times for which I have to apply these vectors T1, T2, Tz. Now, if you have these 3 information, you can simply keep on replicating that whatever vector sequence you want. Say conventional space vector PWM, you can have this or this. Correct? Now let us see how it is coming over there. So we have frequency given that, okay, we are operating at 20 Hertz. From frequency we can obtain the angular frequency omega. There is no problem in that. Multiply by 2 pi only. Then you integrate this angular frequency and what you will get over here?
Theta.
Theta angle.
So theta is what? Theta is the angle which is associated with this vector starting from this point. Theta equals 0 and it is going all the way up to this. Fine?
Yes, sir.
Fine. Now, we know this theta, then we can say that if my theta is within this boundary, it basically belongs to sector 1. if it is within this boundary, 150 to 210, it is sector 2. If it is this boundary, 210 to 270, it is sector 3. If it is within 270 to 330, it is sector 4. 330 to plus 30, this is sector 5. And lastly, from 30 degree to 90 degree, it is sector 6. So we have got the information about the sector from our theta. Correct?
Yes, sir.
Fine. Now the next step would be to get to know what is my sector angle. So let's say this is your theta, which is all the way going from 0 to 360. But sector angle will change only from 0 to what value?
60.
60. So it is nothing but theta sector, or we are calling it gamma, is nothing but mod value of the theta taken against the 60 degree. So what this will result into? This will result into 6 repetitions of the gamma 6 times within one theta cycle. Something like this it will repeat. 0 to 60, 0 to 60, 0 to 60, it will repeat itself. Understanding my point?
Yes, sir.
Correct?
Yes, sir.
This is the information about gamma. Now what we know that in which sector we are and what is the sector angle at the given moment. Say, for example, you are in sector 1 and your gamma is changing from 0 to 60 degree. Now the meaning of this delta sampling is that we are realizing a sample for this much or over this much duration. So if I take simple case P equals 9, that means what? My delta sampling will be 20 degree. Which means what? While the vector is rotating from 0 to 20 or 20 to 40 or 40 to 60, I will have to apply the vector sequences one by one. Okay, I'll bring that, I think. The So what I'm trying to say over here, that the meaning of delta sampling is that we will realize one sample in this range from 0 degree to 20 degree. The next sample will be realized between 20 degree and 40 degree. Then the next sample will be realized between 40 degree and 60 degree. How? By applying the vectors 0, then 1, and then 2, and then 7 in sequence. But we know that we are computing the dwell time. How do we correlate with this changing angle gamma? Again, same thing you can do. Time and angle are related through our angular frequency. So this T1 basically corresponds to angle which you can call theta 1, which is associated with vector 1. So theta 1 is nothing but omega times of T1. Then similarly T2 can be correlated with theta 2, which is basically omega times of T2. This is for vector V2. And theta Z basically means the correlation for 0 vector, which is the 0 vector dwell time, which is Tz. Now what I'm trying to say that once you have this information, you have the total theta, you have the sector theta. Within that you can have one more division, which is sampling angle. So within this sector angle, let us say it is going from 0 to 60 and repeating 6 times within one fundamental cycle. You can have 3 sampling durations because we are realizing pulse number 9, and this I can call delta. Now, what are the values of these points? What is the value of this point?
20, 40, 60.
No, 20, 40, 60 is not needed. Just 20, right?
Oh, yes.
We have divided this 60-degree interval into 3 parts, each having a duration of 20 degree. You understand my point?
Yes, sir.
Yes.
Now, the sequence what we have to apply 0, 1, 2, 7, we have to apply within this duration once, then again within this duration once, then again within this duration once. If I call this angle as delta and the maximum value as delta sampling, what we will effectively do that we will apply when my delta is between 0 and theta z by 2, I will apply vector 0. When my angle is changing from theta z by 2 to theta z by 2 plus theta 1, I will apply V1. When my angle is changing from theta z by 2 plus theta 1 plus theta, from this point to this, I will apply V2. And when this is changing from this to the final value, which is delta sample, I will apply V7. You understand the point? Vector is continuously rotating. What we are doing in response to that, we are applying V1 for this much duration, V0 for this much duration, V1 for this duration, V2 for this duration, V7 for this duration. You understand my point?
Yes, sir.
Now, because you are applying these vectors in sequence over this duration, your resultant vector will be lying somewhere at 10 degree. That is the meaning of that. So if I draw with black, the resultant vector, that will be here. It is the resultant of what you have applied throughout this duration. Are you getting my point?
Yes, sir. Yes, sir.
That is the meaning of sampling at 10 degree. Again, same thing, when you apply the same sequence, let's say 0, 1 to 7 or 7 to 1, 0, all the way from this point to this point, the resultant vector will be lying in the middle here. Because which is what we are computing it for. The T1, T2 dwell time are related to this position. That's why the resultant is here. Getting my point? And the last point will be over here, the last sample. Do you understand?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
See, from scalar to vector, the difference is that we are dealing with magnitude as well as the direction. Here it's only magnitude. We have applied something for these two durations, we have got the answer. But here we are giving vectors. Now for scaling that, we are multiplying the time, dwell time with that, or you can say theta. That's also correct. There is no problem in that. So this is what we are getting in response to what we are applying. That's another meaning of what is the sampling interval or sampling position. You understand or not?
Yes, sir.
Yes, sir.
Okay, see here closely. This is for pulse number 9. You see this small dot which is moving. This is your voltage vector which is continuously moving. It's going in continuous circle. What we are doing, as it is moving from one sample period, during one sample period, we are applying the vectors. Say, for example, from here, this point to this interval, we have applied 0, 1, 2, 7. And the resultant would be this vector which is lying in this sample. The voltage vector is rotating continuously in response to our theta, what we have generated. And what we are doing, as it is rotating from one point to another point, we know it belongs to which sector, which sample, and we are applying the vectors appropriately based on their dwell time. Here, dwell time we have translated to theta. And so we are applying that. And in response, we are getting these vectors, which you can call, okay, these are the samples of what you have got over here. You understand my point?
Yes, sir.
This circle is basically the trajectory of tip of the voltage vector. The big blue lines, these are basically your active vectors which you are applying along with the zero vectors which are at center. And red are the vectors which you are realizing out of this. Fine?
Yes, sir.
So better the pulse number is, let us say now if I take only pulse number 3, which is one sample per sector, what will happen? For 60-degree duration, you will have only one sample, which is of course very crude approximation, very incorrect approximation. There will be huge ripple. So as it is moving from one point to another point, we have only one sample to realize. That's very crude approximation. Whereas something like if you go for very high pulse number, say 45, so you see how smooth this will look like. How smoothly we are realizing each and every voltage vector which is coming as a sample. So more number of samples if you have, the better approximation you are doing for the voltage vector which is rotating on the circle. Do you understand this point?
Yes, sir.
Yes. Yes, sir. Yes, sir.
Clear what we are trying to do now?
Yes, sir.
Anybody having any confusion? Okay, just to repeat that. The tip what you see over here which is rotating, the small triangle over here, this is basically tip of the voltage vector which is continuously rotating as your voltage is fed to the machine or as your motor is running. We are trying to approximate this continuous rotation with certain snapshots, with certain voltage vectors which are taken at regular intervals. And these voltage vectors are realized by applying the blue vectors which are shown over here. Blue vector in addition to the zero vector which is at the center. Fine. That's the whole crux of space vector PWM. Now, in what sequence we do, how we apply the vectors, that makes the space vector, as a conventional space vector or something else, the name goes differently. So this point is clear to all of you, right? For implementation, you need to know only these angles. First, what is the fundamental angle? Then what's the sector angle? Then what is the sampling angle within this? Now, for this sampling angle, which is varying from 0 to delta sample, you are applying these vectors for the durations which you have computed. Fine? Is it clear or not? Tell.
Yes, sir.
Yes, sir.
Yes, sir.
Fine.
Yes.
Deepak, is it clear now?
Yes, sir.
Okay. Now we move to the next question. How do we apply the vectors? So we have one option we have set for conventional space vector PWM, that we can apply similar to sine triangle PWM. What do we have in sine triangle PWM? We have the carrier falling like this, and we have three modulating signals, say these two and then somewhere here. So what happens? Ultimately, we are having either the plus 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 vector applied first, then plus plus minus, plus minus minus, or minus minus minus. This I'm talking about sector 1. So maybe this is not appropriate way to draw. R should be maximum, B should be the minimum. So let's draw R here and Y here and B here. So this is what we are kind of looking for, right? So what do we have basically? That we are applying these vectors in sequence, or we may have, let's say this is falling carrier, we may have a rising carrier. That will result into the vector states minus minus minus, plus minus minus, plus plus minus, or plus plus plus. So it's all going in sequence, either 7210 or 0127. And we know that the sample what we have created can be realized by having any of the two combinations, 0127 or 7210. Now, if in any sector we have multiple sample, if there is only one sample, let's say pulse number 3, no problem. You can have either 7210 or 0127. Once you go to next sector, only thing you have to keep in mind is that there should not be any multiple switching when you go from one point to another point. It's better to bring this. So let's say pulse number 3, we have only one sample. So either of the options are okay. Oh, what has happened? Now, what about the next sector? Again, this will have sample over here. What would you apply? Say you have chosen that, okay, you will apply 0127. So what should be the corresponding sequence for the next sample?
It should be, sir, 7230.
Correct. So 230. Why 230? Because the vectors associated with this sector are 2 and 3. Correct. Now why 7230 and not 0237? Because we are ending this sector at the vector plus plus plus. So we should start the next sector with the vector plus 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 only. We cannot have starting with minus minus minus. There 3 switchings are involved. So we must have 7 coming at the beginning. And then the next sector, this will be beginning. So 0, 3, 4, 7. Then next sector will start with 7, 4, 5, 0. Then the next sector will go 0, 5, 6, 7. And then it will come over here as 7, 6, 1, 0. And then it continues. Do you see that? So first thing we have to avoid is any multiple switching, which is avoided by having the same 0 vector applied in the next sector in sequence. We do not change the 0 vector abruptly. We continue with the same 0 vector. Fine. Now, if we have multiple...
Sir, can we change T1 and T2? Like,
Sir,
because we say 0127 or 7210.
Yes.
Then it should be 7320, right? In the second sector.
Okay, again we have to see, always we apply the nearest vector. So what is the vector over here? This is plus minus minus, plus plus minus. minus plus minus, minus plus plus. Then what else we have? Minus minus plus. Now you see, whenever we are writing the zero vector which is close to the active vector, it is not having just one switching away from the active vector. It's not having multiple
Yes, sir.
switchings.
Yes, sir. Understood.
So when I write 0, 1, 2, 7, 0 and 1 are only one switching away, 2 and 7 are only one switching away. Similarly, here 2 and 7 are one switching away, but 7 and 3 are two switching away. So we cannot write 7, 3 or we cannot start with any other sequence. Yes, Deepak?
So, but it will be like for half cycle. No? So once you complete the cycle, it will be 0, 1, 2, 7, 7, 2, 1, 0.
There is no other cycle. This pulse number 3 only.
No, sir.
You are muted. You are muted.
This is for one sub cycle, 1 by 2 of switching cycle.
Yeah. So now this is only 3 cycles in one fundamental cycle.
Okay.
You see this, right?
Okay,
One
understood.
sub-cycle itself is coming from 0 degree to 60 degree, or I think, yeah, 0 degree to 60 degree.
Understood, sir. Understood. So,
Correct?
okay. You are only taking 3 switching.
Yes, yes. Pulse number 3 only. Now, so this is how we are picking up. You understand this point, right? 0, 1 to 7 we are going. If we are starting with this, then we must continue with 7 over here. And then the nearest active vector is 2 only. Then the nearest active vector is 3, the next active vector. And then the nearest zero vector is 0. And then continue with 0. Then go in the sequence. And the computations, T1 is always associated with the vector which is starting the sector boundary. T2 is always associated with the vector which is closing the sector boundary. So if T1, T2 are for vector 1 and 2 in sector 1, T1 and T2 will be for vectors 2 and 3 for sector 2. You understand this?
Yes,
Yes,
sir.
We are
Yes,
going
sir.
in this sequence. In this sequence, whichever vector in the sector, whichever vector we encounter first, that is our starting vector. And the computation of T1 is valid for that vector. So if we are in sector 1, the T1 is valid for 1. If we are in sector 2, T1 is valid for 2. If we are in sector 3, T1 will be valid for 3. So it depends on in which sector you are operating. Understanding my point? Fine.
yes, sir.
Yes, sir.
So or shall I write starting vector, closing vector, and the dwell time. So starting vector for, let's say, sector wise we are writing 1, 2, 3, 4, 5, 6. What do we have? We have 1, 2, 3, 4, 5, 6, and this starts from 2, 3, 4, 5, 6, 1. Dwell time, I think I should write here because this is common for all. Here, this is common for all. You understand? T1
Yes,
dwell time is associated with the vector which is starting the sector, and T2 which is closing the sector. Fine? Clear?
Yes, sir.
Okay, now let us say we have more than one sample. So what option is? Option is pulse number 9. So how many samples we will have for pulse number 9? 3 samples. I hope now there is no confusion regarding this sample. What is the meaning of sample, right? That's pretty clear to all of you. Because it is easier to talk in terms of sample, so that's why this definition is required. So our samples are located here. For each sample, we have computed this separate T1, T2. This also has T1, T2. This also has T1, T2. Fine. Again, the next sector will also have 3 samples. each located at respective 10 degree, 30 degree and 50 degree sector angles. Fine.
Yes, sir.
Now, here what you do. Here also you have option that you can start with any sequence. Let's say 0, 1 to 7. So if you start with 0, 1 to 7, you can have this sequence to realize this vector over here. The next one, same rule applies here also. You have to continue with the 0 vector which is ending this sample, which means 7. Then the next active vector is, or closest active vector is 2. Then 1, then 0. Now again you have to continue with 0, 0, 1, 2, 7. So 3 samples will have this kind of vector sequence. You cannot have 0, 1 to 7 all 3 places because you will encounter 3 switching when you jump from 7 to 0. So you must continue this. Correct? This is equivalent to, instead of having a ramp, you have a triangle for the carrier. These two things are equivalent. Ramp will also have your sudden jump in all 3 switching states. This triangle will smoothen that. Triangle will change one by one. That's the same thing which we are doing in the space vector domain. Fine?
Yes, sir.
So now once you complete this sequence over here 0, 1 to 7, what next?
Seven two three zero.
Yes, because it has to start with 7. Now after 7 the nearest active vector is 2. Then the next active vector is 3. Then the next active vector is, next 0 vector or the closest 0 vector is 0. And then it will continue with 0, 0, 3, 2, 7. Then with 7, 7, 2, 3, 0. Any confusion here?
No, sir.
Then once you enter the sector 3, again you have the samples at 10, 30 and 50. So it will start with 0. That is where it has ended. So 0, 3 and then 4 and 7. Then it goes to next, starting with 7, 4, 3, 0 and then 0, 3, 4, 7 and so on. It will continue and you will see that the last sample which is in sector 6 will actually have the sequence of 7, 6, 1, 0. So 0 will continue from here. That will automatically happen. Are you getting my point?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, let us say we may have any number of samples, right? We may have pulse number 15, 21, 27, anything could be there, 33. How long you will keep managing like this, one by one? No, there has to be a method that whatever we do in one sector should be applicable to all the sectors. Isn't it? There should be a way to do that, right? To generalize this. Are you getting my question?
Yes, sir.
Okay.
Yes.
So what we do, let us generalize the sector itself. So what do I do? Instead of writing the number for this sector, I will write only starting and ending names. Let's say the starting vector is A and the ending vector is B. Say, for example, and the 0 vector which is closest to A is called ZA and 0 vector which is closest to B is called ZB. Fine. This is simple, right? That is what we have in all the sectors. We have 2 active vectors and 2 zero vectors, each of which are close to the other active vectors, right?
Yes, sir.
Yes, sir.
Now, if you have to write sector wise, say sector, and then what is the vector A, what is vector B, what is vector ZA, what is vector ZB, you can very easily write similar to what we have wrote in the previous table. So always the starting vector for sector 1 is 1 and then it goes in sequence. Similarly, for closing vector, it just starts with vector 2 for sector 1 and then goes in sequence. Now, the 0 vector which is closest to the active vector 1 in sector 1 is basically 0. And the 0 vector which is closest to the closing vector in sector 1 is basically 7. In the next sector, you will find that these two are flipping. You understand my point?
Yes, sir.
Yes,
Now,
sir.
I tell that if you are implementing conventional space vector for this, three-phase, two-level inverter system, what you need to do for the multiple samples, you need to have one of the generalized sequences. What is the generalized sequence? First sequence you can say it is ZA, B, ZB. You apply vectors in this sequence. Or you apply in the other sequence which is ZB, B, A, ZA. These are the two sequences, right? For sector 1 this becomes 0, 1 to 7, 7 to 1, 0. And for each sample you keep changing this. Let's say for sample 1 you keep this, sample 2 you keep this, sample 3 again you go back to sample 1. So you keep changing between the two, alternating between the two within a sector. And from this lookup table you keep picking up the vectors properly for the corresponding sector. You will find that only with this much effort you will be able to realize the complete space vector. Understand the point, or this is going a little bit heavier? Tell.
No, sir. Clear, sir.
Clear for everyone?
Yes, sir.
Yes, sir.
Okay, lot of people have dropped out, or everybody is there? Not able to see all 12 people on the screen. What happened to other 6 or 5 people? Or 4 at least?
Sir, I rejoined through phone.
Yeah?
My laptop got discharged, so that I rejoined through mobile phone.
Okay, okay. What about others? Uday? Deepak?
The data problem is that is why like video was consuming more data in between.
See, I need to see your faces to understand whether you are getting anything or not. So please tell, if you are not able to turn on your camera, then please respond at least. Okay, so this point is clear, right? Now I leave it here up to you. Once you start implementing in the simulation what I have given now, you will understand more about it. So once you generate any confusion over here, if you find any trouble, come back, we will discuss it again. Good? Okay, so one last point I will give for the space vector PWM is what is the maximum voltage which you can realize using the conventional space vector PWM. And we are talking about this conventional space vector, which means any of the bus clamping and all these things are not there. So simple sequence 0, 1 to 7 or 7 to 1, 0, either of this is involved for realization of samples in the sector. Now, the question is that what should be the limit of maximum voltage which we can realize on this using the conventional space vector PWM? So our voltage vector is basically what? It's a circle that's concentric with the hexagon, and the voltage tip of the voltage vector is rotating on this circle, as you have seen just now. Now, by magnitude, I mean how much the size of this circle could be. Can it go bigger than this hexagon? Something like this?
No, sir.
So how much it could be? Where is the
Just
boundary?
touching the inner
Touching.
portion, inner
Okay.
side. So
Let's say touching the inner hexagon boundary. Okay. How do you get this? What is the
Sir-
way to interpret this?
sir, in
This
that
is-
case, we don't apply any zero vectors. Only the active vectors will be applying for
Okay,
half of the time.
let me take the sample here at 10 degree. Would you not apply the zero vector? For which sample you are talking about, you would not apply
Sir,
the zero.
I was talking for around 30 degrees.
Why? Question is why? It is correct. What you are saying is correct. That the maximum voltage amplitude what we can realize using the space vector is this circle, inner circle, which is touching the hexagon boundary. Now, how do you get that? The simple answer could be that point where our value of Tz goes to 0, which means without applying the zero vector, we are able to realize the vector. That is the maximum we can do. Correct? Which means our T1 or T2 have reached the limits. We cannot cross any further. You understand my point?
Yes, sir.
Yes, sir.
Correct. Now, if you see the contribution of T1 and T2, this is, let's say I draw 3 samples, 10, 30 and 50. At 10 degree, you will see that contribution of vector 1 is large. This is more compared to 2. And definitely there has to be some zero vector, because this is only small amount or small duration this is needed. So rest of the time we need to fill with the zero vector. Here also similar scenario. The major contribution for this sample is from vector 2. One is having lower contribution and rest of the gap needs to be filled by the zero vector. Whereas a point which is in the middle at gamma equals 30 degree, this is where we find that the contribution of T1 and T2 are equal. Fine. That's what the expression we have seen, right? T1 equals V1 by VDC sine 60 minus gamma by sine 60 Ts. And the other one is T2 Vs by VDC sine 30 by, sine gamma basically. So these two are going to be equal for gamma equals 30 degree. Any doubt in this? That's the general understanding. This vector sample is in the middle of the two. So contribution from both are going to be large or significant or equal, we can say. It is equal basically. Now this is where if we can equate our zero vector to the value 0 or the Tz value to 0, which means the maximum utilization of V1 and V2 are achieved. Understand my point? There is nothing further we can do. We have 0, 1, 2, 7. Now, if 1 and 2 are equal, say T1 and T1, and this is Tz by 2, Tz by 2. Maximum value of this T1 could be Ts by 2. That's the meaning of Tz by 2 going equal to 0, right?
Yes, sir.
So this is where we say that our limit for realization of voltage vector has reached. We cannot get anything more than this. We cannot apply anything more than this time duration. So that's the boundary of our conventional space vector PWM for linear modulation. If we go anything beyond that, we will be going into over modulation. So now for this, there are two methods you can solve. One method is that you compute this length of this arc from this triangle. So let's say if I write the name O, A and B. So this OA is basically having length VDC. AB is having length VDC by 2. So you can compute OB, which is basically our magnitude of the maximum voltage vector. This will turn out to be √3 by 2 times of VDC. Fine, that is one way. Or simply you can equate from here the time durations. You equate T1 and T2 both equal to Ts by 2 and you will achieve the same value, sine 30 by sine 60 times of Ts. So this will give you Vs max equal to √3 by 2 times of VDC. These both will give the same answer. And that's the meaning and physical relevance of what we are doing. You understand the point?
Yes.
Yes, sir.
Now, once we have done this, so this is voltage vector. What is the peak value of fundamental voltage what we are getting from here? That is what I think, Tejdeep, you were asking, right? How to correlate the peak value with this vector. Fine. So we know that we are doing the three-phase voltage vector transformation to alpha beta and then all this. So V alpha and V beta, both we are finding that magnitude is equal to, for sinusoidal input, 3 by 2 Vm sin omega t and minus 3 by 2 Vm cos omega t. So for the sine wave having peak Vm, the Vs vector magnitude, if you see, it will turn out to be 3 by 2 Vm. Correct? So that is how these are related. The peak phase voltage and the peak of the vector or the vector magnitude. So if this is our peak, magnitude of the voltage vector, the peak phase voltage will be basically related to the peak phase voltage like this. I can write V phase. Understanding my point? So this is where we can relate the peak phase voltage with our maximum voltage vector what we are realizing in terms of DC bus voltage, and it will turn out to be
DC by
√3 VDC by √3. Yeah.
Yes, sir.
So here we find that our DC bus utilization is 57.7% for space vector PWM. Fine. This is clear, right?
Yes, sir.
Now, very general question comes to our mind. Sine triangle also we are applying 0, 1, 2, 7, 7, 2, 1, 0 in sequence. Space vector also we are applying 0, 1, 2, 7, 7, 2, 1, 0 in sequence. Here we are getting the DC bus utilization as only 50%, VDC by 2. Here we are getting VDC by √3. Why?
Like null vector division will not be equal in the case of sine triangle PW.
Yes.
But in this case, in conventional we split the two into equal half.
Correct.
Yes, sir.
This is very correct explanation. Now, do you understand that this is not equal, or just saying because you have heard it somewhere?
So if we analyze from the waveform, three-phase waveform, when R phase is at maximum peak, at that instant the other two phases are not in the negative maximum. That's why the zero voltage duration is not coming equal.
In fact, it is true for any duration. It's not necessary that you analyze for the peak value only. See, our problem is with sine triangle that we have to maintain MR plus MY plus MB equal to 0. Correct? If we talk about sector 1, where the R phase is maximum, say at point 0.8, maximum value. Then if our y is, let us say, at minus 0.2, so b is bound to be at minus 0.6. It cannot be 0.8, right? Because
Yes,
we have to have three-phase balance system. So if I have to compute the dwell time out of this, or the duration for these different intervals, this tz1 and tz2, it cannot be equal, because we are talking about different height at these two locations. Okay, maybe this should go a little higher. We are talking about 0.8. So maybe it's here. So it cannot be equal. That's the point. This is somewhere 0.8. Because these two heights, the difference here and the difference here, which is basically corresponding to this gap, these are not equal. That's why in sine triangle we cannot achieve same dwell time for the zero vectors. Now what to do for that? That is where we try to yes,
Common mode.
yes. So this is where we try to realize the conventional space vector in or
Carrier,
with,
yes.
you can say, with triangular carrier. Or in other words, we say that equivalent of conventional space vector PWM in sine triangle PWM. So of course we need to do something over here. Let's say if you shift all the three waveforms by certain amount, say I shift all by equal values. Is it going to change my durations T1 and T2? Is it going to change?
No, sir.
No,
No, sir.
because this difference remains same, which is responsible for these T1 and T2 dwell times. These durations are, or these gaps are going to remain same. What will change basically? The value which is now coming over here. Correct? Say we have added some common mode, and if let us say this is MR, MY, MB, or in general we have also seen that always there is one phase which is having maximum value. In each sector we have seen that one will have minimum value and one will be in the middle. This is always going to be true. So we have, after addition of this common mode, we have new modulating signals which are basically star, we can call M max star, M mid star, and min star. So now this is what we are trying to do. We are trying to make TZ1 equal to TZ2. Have you done this exercise, Tejdeep?
Sir,
Is this exercise already covered somewhere?
sir, like we implemented that like CSV based PWM.
No, that you implemented, but this exercise, the computing the common mode.
No, sir.
Okay, so quickly, maybe another minute I will take to cover this, and you can do on your own also. Now what we are trying to do, we are trying to equate height which is coming over here and coming over here. Now what is this height basically? This is 1 minus M max star by 2, let us say, the ratio of this and this total height. And similarly, this small height over here, which is 1 plus M min star, I am taking the magnitude because time cannot be negative. So we are always taking magnitude. And again, ratio of the total height. These two ratios we are trying to equate, which means what basically? We are trying to have M max star plus M min star equal to 0. This is what is the ultimate purpose, basically making both the heights equal. So M max is nothing but the original M max plus the common mode which is added. And M min star is nothing but M min plus the common mode which is added, and both going to 0. So from here we get information about the M common mode is that it is nothing but negative of half of M max plus M min, or in other words we can say this is M mid by 2, because M max plus M min plus M mid is also going to be 0. So this is our common mode which we see in our equivalent of the space vector PWM. If you want to implement that, which is your next exercise in the lab, so this is the common mode which you need to add. And this common mode, if you try to plot, it will look like a triangle. So something like if you have this as the full cycle, so something like this triangle it will look like. And when you add this common mode to our modulating signal, this will also become different. Something like this. So a more proper drawing maybe I can show. So this is how it will look like. So what you see over here in the violet, that is basically the common mode which is generated. It's not third harmonic, it's basically combination of all the third harmonics. 3, 9, 15, 21 and all. It's not just one third harmonic. Okay, and this is the resultant modulating signal what we would get, which will give equivalent DC bus utilization for our triangular carrier based PWM. And not just DC bus utilization, but also the best current ripple. In case of third harmonic injected, we have seen either we can get the best DC bus utilization or we can get best current ripple. Here, this has the capability of give both together. Fine?
Yes, sir.
Good. So we have covered a lot of things today. Tomorrow I will try to go for some other PWM techniques in space vector and how to analyze the current ripple, torque ripple and all these things. So, and Friday and Saturday also I would like to take the class. So if any of you are having any commitment, you can inform me.